Hello friends and dear students, I welcome you all to my channel. I hope you are all well and your studies are also going on well. In this part 9 video on the concept of limits, I will discuss about the standard results of limits related to tan x, related to the function tan and tan inverse. This video is part of the playlist Problematic Mathematics for class 11, where I primarily discuss about the key concepts and formulas targeted towards solving problems that comes in the competitive examinations like JEE Mains, JEE Advanced or WBJEE. If you find this video beneficial, then please like it, share it with your friends, and please support me to grow my channel. Subscribe to my channel and do not forget to press the bell icon so that you will be notified by my future videos. Okay. So in the previous video I discussed about the standard results of sine function sine and sine inverse. That is, we discussed about that limit sine x by x, limit x tending to 0 sine x by x is 1, and also limit x tending to 0 sine inverse x by x is equals to 1. Instead of x, it could be fx, that is limit of fx tending to 0 sine fx by fx is also equals to 1, and limit of fx tending to 0 sine inverse fx by fx is equals to 1. And I discussed about the actual tending values of sine x by x when x tending to 0 and sine inverse x by x when x tending to 0. So if you have not watched the previous video, please do watch it. You will have a good concept of the standard result of sine x by x when x tending to 0, or in general sine fx by fx when fx tending to 0. In this video I will discuss about the function tan and tan inverse. So you must be familiar with the standard result that let me configure my writing software. Okay. So the standard result you must be familiar is that limit of x tending to 0 tan x by x is equal to limit x tending to 0 x by tan x is equal to limit x tending to 0 tan inverse x by x is equal to limit x tending to 0 x by tan inverse, and all these limits are equal to 1. So this is the standard results we all know, but in the general form of the standard result is that instead of x it could be any function of x, that is fx, but when fx tending to 0 at the tending value of x, given tending value of x in the problem, if fx tending to 0, then the general form is that, okay, so let me write it. The general form is that limit of fx tending to 0, whatever the tending value of x is, in that at that tending value of x, if fx tends to 0, so that is what in short it is written as limit when fx tending to 0 tan of fx by fx is equal to limit fx tending to 0 fx by tan of fx is equal to limit fx tending to 0 tan inverse fx by fx is equal to limit fx tending to 0 fx by tan inverse fx. All these limits are equal to 1. Okay, now we need to understand one thing very clearly, is that when x tends to 0, this implies that tan x by x, this tends to 1 positive, that is the actual value of tan x by x is a little more than 1 when x is tending to 0. Now why is that? You can we can prove this using L'Hopital's rule. So but since when x tending to 0, the value of tan x by x tends to 1 positive, and in the limiting in the terms of limit, in the limiting language, we say that limiting value of tan x by x when x tending to 0 is 1. But why is that tan x by x tends to 1 positive when x tends to 0? The basic foundational concept is that cos x x tending to 0 when x tends to 0, this implies that cos x will tend to 1 negative. That is, the value of cos x is little less than 1 when x tending to 0. That is, in both cases, when x tending to 0 positive or x tending to 0 negative, cos x tends to 1 negative. That is, value of cos x is little less than 1. Okay. Now, so if I take the derivative of, if I take the, so tan x in finding the limit of tan x by x, so limit x tending to 0, tan x by x, it is of the form 0 by 0. It is of the form 0 by 0 because when x tending to 0, tan x tends to 0 and x tending to 0. So this is 0 by 0 form. So using L'Hopital's rule, this is equal to x tending to 0, 6 square x by 1. Okay. Now, so when x tending to 0, we know that when x tending to 0, x tending to 0 implies that cos x will tend to 1 negative, that is a little less than 1. This implies that cos square x will also tend to 1 negative, that is it will be a little less than 1. But then if I take the reciprocal, 1 by cos square x will tend to 1 positive. This implies that sec square x will tend to 1 positive. So we see that when x tending to 0, sec square x is tending to 1 positive. So clearly now this we can say that limit x tending to 0, sec square x will actually sec square x will tend to, so this limiting value will tend to 1 positive. So that is the reason we see that when x tending to 0, tan x by x actually tends to 1 positive. But in the limiting, in the language of limits, we say that, so we say that this implies that limit when x tending to 0, tan x by x is equals to 1. But remember that when x tending to 0, tan x by x tends to 1 positive. This is important because when x tending to 0, this implies box of tan x by x will tend to box of 1 positive. Now box of 1 positive is equal to, not tending to, but equal to 1 is equal to 1. Okay. But when x tending to 0, this implies box of x by tan x will tend to box of now if when x tending to 0, if tan x by x tends to 1 positive, then definitely x by tan x will tend to 1 negative, which is equal to box of 1 negative. 1 negative means a little less than 1 is 0. So then we can say we will see that when limit x tending to 0, box of x by tan x is nothing but limit x tending to 0, the box of x by tan x will become 0. So this is 0. So we see when we apply, when we put x by tan x inside the box, the limiting value of box of x by tan x when x tending to 0 becomes 0. If the box was not there, then the limiting value would have been 1. So you must be very careful about this, that tan x by x tends to 1 positive when x tending to 0. Obviously then x by tan x will tend to 1 negative. Okay. Let's see, now this was tan, function of tan. Let's see tan inverse. So when x tends to 0, this will imply that tan inverse x by x, this will tend to 1 negative. The value of tan inverse x by x will tend to its value will be a little less than 1. We can again see these results using L'Hopital's rule. Okay. So let's say we are finding x tending to 0, tan inverse x by x. Using L'Hopital's rule, this becomes limit x tending to 0. What is the derivative of tan inverse x? It is 1 by 1 plus x square, and we have derivative of x is 1. So this is limit x tending to 0, 1 by 1 plus x square. Now x tending to 0 implies that x square will tend to 0. This will imply that 1 actually it will be 0 positive. So then 1 plus x square will tend to 1 positive. This will imply 1 by 1 plus x square will then tend to 1 negative. You see, that is the reason we say that tan inverse x by x tends to 1 negative when x tending to 0. This will be important if there is a box, if tan inverse x is put inside a box. So this means that limit x tending to 0, box of tan inverse x by x, this will be limit x tending to 0. Now box of tan inverse x, when x tending to 0, tan inverse x by x is tending to 1 negative, that is its actual value will be a little less than 1, and then the box of, so this is the box of 1 negative, and this is equal to limit x tending to 0, 0, which is equal to 0. So this result you must be very careful about, that limit x tending to 0, box of tan inverse x by x, limiting value of box of tan inverse x by x when x tending to 0 is 0. But if the box was not there, then the limiting value would have been 1. Actually, the limiting value of limit x tending to 0, box of tan inverse x by x is actually exactly equal to 0. It is not tending to 0, but exactly it is equal to 0. So this was the basic concept of the standard results of tan x by x and tan inverse x by x, and instead of x it could be fx tending to 0. Now let's see now if what will be if we are asked to find, let's say limit of tan of fx by gx when whatever the tending value of x is, at that tending value of x, both fx and gx is tending to 0. That in short form is written as fx tending to 0 and gx tending to 0. This will be the concept is same as sin fx by gx. I will create fx in the denominator and I will adjust it. So this is equal to fx tending to 0, gx tending to 0, tan fx by fx multiplied by fx divided by gx. So limiting value of tan fx by fx when fx tending to 0 is 1. So this becomes 1 multiplied by limit fx tending to 0, gx tending to 0, fx by gx. It will be of the form 0 by 0, and probably you can find this limit using L'Hopital's rule. Now remember that you will apply this method only when the limiting value of fx by gx, when both fx and gx are tending to 0, exists and it is a finite value. In most cases, you will be able to solve this kind of problem using this technique. Same is the case for tan inverse. So limiting value of fx tending to 0, gx tending to 0, tan inverse. If we have this kind of limiting problem, tan inverse fx by gx, I will create fx in the denominator and I will adjust it. So this becomes limit fx tending to 0, gx tending to 0, tan inverse fx divided by fx multiplied by fx divided by gx. So this is again tan inverse fx by fx, a limiting value of tan inverse fx by fx when fx tending to 0 is obviously equal to 1, and we have this equal to limit fx tending to 0, gx tending to 0, fx by gx, which will be of the 0 by 0 form. Since both fx and gx are tending to 0, whatever the tending value of x is given in the problem, using L'Hopital's rule or any other methods, you can in most cases you will be able to solve this limiting value. So you can apply this technique. Now again, you might be given a problem. Let's say now limit x tending to 0, tan x to the power m divided by x to the power n. So again this is similar to the limiting value of sin x to the power m divided by x to the power n when x tending to 0, which I discussed in the previous video. You can watch that previous video. So this is equal to limit x tending to 0, tan x by x whole to the power m multiplied by x to the power m divided by x to the power n. This part limiting value of tan x by x whole to the power m, where m and n are natural number. Over in this problem, m and n are natural numbers. So this part will become 1. So this is equal to limit x tending to 0, x to the power m minus n. So this will be equal to 1, exactly 1, not tending to 1, but actually exactly 1 when m is equal to n, because if m is equal to n, m minus n is 0, and x to the power 0, remember the power 0 is exactly 0 when x tending to 0 is always 1, exactly equal to 1. Now this will be if m is greater than n, then this will be 0 because for when x is tending to 0, x is not 0. When x is tending to 0, then x to the power n, where n is some natural number, x tending to 0 will imply that x to the power n, where n is a natural number, will tend to 0. So this will be 0 when m greater than n, and it will be infinity when m is less than n, because if m is less than n, then m minus n will be a negative integer, and it will be then 1 by whatever them. So this will be then it will be 1 by x to the power n minus m, and it will be so why is it is infinity when m is less than n, because x tending to 0 implies that when m is greater than n, I can say x to the power m minus n will be 1 by x to the power n minus m, So n minus m is will be a positive integer, and this will be tend to 1 by 0, which will tend to infinity. Okay. Now what else? Another some pattern of question could be like, what if you are asked, let's say limit x tending to 0 let's say sine of fx by sine of gx. This could be a particular pattern of problem where actually not x but fx is tending to 0. That is, whatever the tending value of x is given in the problem, at the tending value, if fx is tending to 0, that is in short written as limit fx tending to 0, and we have the function as f sin fx divided by sin gx. Actually both fx and gx tending to 0. If both fx and gx tends to 0 at the given tending value of x, then how do we solve this limiting problem? That is sin fx by gx. Nothing, it is very simple. We will create fx, we will create sin fx by fx, and I will create sin gx by gx, and I will adjust fx and gx. So this is equal to limit fx tending to 0, gx tending to 0, sin fx, I will create fx, I will adjust fx, and then we have divided by sin gx, I will create gx, and I will adjust gx. Now when fx is tending to 0, then obviously limiting value of sin fx by fx will be equals to 1. So this becomes limit, and also when gx tending to 0, then the limiting value of sin gx by gx will be equal to 1. So this becomes limit fx tending to 0, gx tending to 0, we have fx by gx. Obviously, since fx and gx both are tending to 0, this is of the form indeterminate form 0 by 0. Hopefully, in most cases, you will be able to solve this limiting problem using L'Hopital's rule. Okay, this was one pattern of problem. This will instead of sine, it could also be tan, that is limiting value of tan fx by tan gx. When fx and gx tending to 0, you can apply the same exact technique. Now what if we have a problem like this? The basic fundamental technique is same. Let's say we have fx tending to 0, we have sine of fx divided by tan of fx. Remember, both the tan, sine, argument to sine and tan is fx, where fx is tending to 0. This is equal to limit fx tending to 0. Again, I will create the sine fx by fx. I will adjust fx. Again, with tan fx, I will create fx, and I will adjust fx. So these fx cancels out. So this is equal to 1 by 1, which is equal to 1. Remember that this is also a very standard result. You can remember that limit of sin fx by tan fx when fx tending to 0 is equals to 1. Okay. Now this could also be something like this. Limit fx tending to 0, gx tending to 0, and we have sine of fx divided by tan of gx. Again, the basic technique is same. I will create sin fx by fx and tan gx by gx, and I will adjust fx and gx. So limit fx tending to 0, gx tending to 0, sin fx by fx, I will adjust fx, and I will create gx, tan gx by gx, and I will adjust gx. Now limiting value of sin fx by fx when fx tending to 0 is 1, and also limiting value of tan gx by gx when gx tending to 0 is 1. So this becomes limit fx tending to 0, gx tending to 0, fx by gx. Hopefully in most cases you will be able to solve this problem because it is of the form 0 by 0. So this is all about the fundamental concepts and related to the standard results of tan inverse, tan x by x and tan inverse by x. Now remember, in this problem sin fx by tan x, fx tending to 0, it could also be sin inverse fx divided by tan inverse fx. The basic strategy is same. I will create fx and I will adjust fx. Similarly for it could be sin inverse fx by tan inverse gx when both fx and gx tending to 0. I will create fx in the denominator of sin fx of sin inverse fx, as well as I will create gx in the denominator of tan inverse gx, and I will adjust fx and gx. It will be, the result will be the same. Ultimately the limiting value will be limiting value of fx by gx when both fx and gx are tending to 0, and you can 99.99% of the cases you will be able to solve this problem using L'Hopital's rule. So that is all for this video. In the next problem I will try to solve few problems based on the concepts I discussed in this video and the previous video. If this video was beneficial, then please like it, share it with your friends, and please support me by subscribing to my channel, and do not forget to press the bell icon so that you will be notified by my future videos. I am ending the video here. Thanks for watching, and until the next video, take care and bye.